If you have any question about whatever we discussed last time, just you can ask now. And if not, we can continue to talk about near transfer. So we said when we discussed near transfer, which is basically the idea in or the belief in the effectiveness of high fidelity simulators, we said that the reason that it's a belief is because it is argued that mental space or psychological space corresponds to the physical space. And if you think about it, it's just something like you can think of it as a Venn diagram, or like two shapes, something like this. But here is mental space. And this one is physical space. So any distance between these two should correspond. So if we have something like this, so each of these are something like skill in the mental space, skill 1, and skill 2. The distance between them should correspond to the distance in the physical space. So here we have, say, two simulators. Simulator 1 and simulator 2. And so this is, say, for two certain simulators or two different systems. System 1, system 2. So these two distances are equal. So here we have in the mental space one skill or expertise, and another one, so say an expertise in playing chess and expertise in solving Sudoku puzzles, for example, or anything of that kind. So the distance between these two correspond to the same distance. So there's an equal distance with the corresponding simulator. So if I practice with simulator 1 and I develop skill 1, and I practice with a different simulator that is this much distant from the first simulator in terms of physical characteristics, then the distance in skills are the same. So this is basically saying that whatever we see in the world, in systems, in different types of systems, in anything that we can perceive, the distance between them is the same as the distance in terms of what we learn or our skill in using them or in operating with them. This is the belief in terms of Venn diagram. It shows how the belief in near transfer exists. So this would lead to the conclusion that higher fidelity systems are more effective. And so the goal becomes to build high fidelity systems. or to have an effective training, we should have high fidelity system because they are very close or near to the physical systems in the world or the target environment. And there are many identical elements or shared elements between them. So that's why we're going to talk about high fidelity simulators or high fidelity systems. And when we use the term high fidelity system or simulator or training system or training simulator, they basically mean the same, at least in our context. Can be different, but when we say training system, training simulator, they're both referring to the same thing. So we know that high fidelity systems are those that look like target systems, that are very realistic. And their realism applies to everything that is relevant to the training or operating in that environment. It is tools or anything that is considered as tools like systems. And of course, the task or the objective of using those tools. And other surrounding elements like locations or other things. And a high fidelity system tries to replicate these elements as realistically as possible. Now we could just continue by saying that, for example, there are other elements like timing, like emotional factors, like stressors and that kind of thing. But at least for having a general understanding of high fidelity systems, what comes to mind at first is their perceptual features. And then when you try to assess them in a deeper level, you can have these factors like stressors, timing, and other things. So one question that I have from you now is that what are the things or what should we know to build high fidelity simulators? Or imagine you have to build or design a high fidelity simulator for training, of course, for a task. What do you need to know? Yes? So basically those simulators or those computational systems and tools that try to implement the simulation. Yes? So you mean an expert or an expert? Okay, yes. Usually, I mean, because here we are more focused on the system itself, that is a required element, of course, but because here we are more focused on the system, imagine we have a system independent of everything else, no expert at all, we don't even have access to experts in this context, and then we want to build that system. And it is assumed that trainees should only work with that system and develop skills, at least over a couple of sessions. How should we build that? Or what are the things that we need to know to build that simulator? Yes.
You need to have a good understanding. No one's brilliant. I mean, you have a good understanding.
Skills that are required. And of course, we discussed things like task analysis and studying experts by observation, video recording. And those are the ways that we gather information about the skills that are needed to implement the simulator. But now I would invite you to think more like in terms of the trainee's experience. Like, imagine you have that target system and target environment, and your goal is to replicate that experience as much as realistically as possible in here, which is far from that environment. What do you need to know? Yes.
I would say if there's like some sort of tool involved, try to make it visible instead of like neutral, so you can get experience of like actually holding it and interacting with it.
Yes, for many, and your name?
Nathaniel.
Yes, for many systems, it's basically higher fidelity simulators involve using like actual materials that is not like, I would say that the more you go toward low fidelity systems, the less you're reliant on those actual materials, and the more you see the 2D simulation or even paper 2D depicting of a system or something like that. So yes, higher fidelity systems often involve or have physical features or physical characteristics of the target environment or system. Any other thought on what we need to know? Yes.
Trying to replicate as closely as possible how some sensors, as few or as many as applicable to be necessary.
Yes, exactly. That's an important point. Our sensory inputs. So we see something in the world. We perceive the target environment. It looks like something. There are different colors, distances of different objects. The system itself has certain physical characteristics. And to build a high fidelity simulation, we need to replicate that sensory experience in the training system. And to do that, we need to know about human sensory system. And that's the goal of the rest of the lecture. So the first thing that we need to know in a more theoretical level is human visual system, because vision is one of the main sensory inputs of human. And so if you think about the human visual system, or particularly the eye or seeing, you can imagine, for example, visual illusions like a mirage. You have to be aware of that. So you don't want to build a simulator that happen to have visual illusions without intending to. And there are many of these visual illusions. Now, this is just an example. Or this is another famous example, that if you look at the squares A and B, they are of the exactly same shape, but they look different because we think one of them is in a shadow, it has a different color or shape, but A and B are exactly the same. So you can think about numerous other examples. If you just search internet, you'll find many examples of visual illusions, and a designer of interface or the training simulator must be aware of these. And sometimes they're intentionally used for certain purposes, but often people try to avoid such thing like these. These are two specific examples, but there can be many subtle things in the design of a simulator or system. And this is not just about training system, but about designing almost all other products in user interface or those who do UX research must be aware of these visual illusions that people have. So now one question is, can you think of other reasons? We talked about visual illusions, but can you think about other reasons that we have to study human vision? Yes?
Back to the example about blind, some training might be colorblind, see color, and depends on what like dial or things they have to use tool-wise, it would be.
Yes, exactly. Colorblind is an important thing. There are many people who are colorblind, or even if they are not colorblind, the recognition of different colors is not exactly like the average people. And your name? Okay. So colorblind is a good example, yes. And it's not just choosing colors in simulator that is important, but also the knowing the trainees population or their needs analysis and their characteristics that we have to take care of. Any other thought? So, as you mentioned, color sensitivity is another thing. I mean, it's relevant to colorblind, but basically for average humans, human sensitivity to colors is the most, for example, in this range of colors. So we can detect small changes of frequency in the electromagnetic frequency level in this range, but then outside of this range, our power is reduced or here. So this is sensitivity, this is the wavelength. This is something to have in mind. You don't have to memorize all of these, but it's just to give you an example of why we have to take care of these factors. Or another example is distance perception. That here you see in A and B, you compare them. In A, the right figure is smaller than the left one. So if we see this, we would say, well, there are two people. The left one is bigger or larger than the right one. But when you just put the same size in a distance, in a dimension, that shows something like a dimension of a space in the B, we would say, well, these two are almost similar in terms of size, because we know that the right one is more in distance. Or if you think about these two, these, again, in C, we see them as similar size, but if we put one of them in distance, we would say because this one, the right one, is farther away, it's highly likely to be larger than the left one. So you can see that if we give dimension to things, our perception of size would be different. Or another one is this, like you see that we are moving, for example, and we see things as passing faster than other things. Those that pass faster are considered to be closer to us than those that pass like slower in the background. So these are some characteristics of human perception in terms of seeing. Or another one is not directly relevant to how we perceive things in terms of like the low level processing, but is more about human background knowledge or our background knowledge. It might be cultural, but it's still things that we see and recognize. But for example, this is like biohazard. People who are familiar with it know. Or think about stop sign. This sign is a stop sign in Japan. We don't even recognize such thing here. So that's why if we want to replicate something as realistically as possible, one of the things that we should know about is the characteristics of human visual system. And in short, the reason to know about them is because of factors such as these that we talked about, like color perception, visual illusion, distance perception, and other things. So basically what we are doing here is breaking down what seems like realistic as why we see them as realistic or high fidelity. Do you have any question about this human visual system and why we need to know about it? Okay. So the second factor is auditory system. Or human ear. And one of the things or main characteristics is the range of frequencies that human ear we can recognize or we can hear. And if you look at this, these are the frequencies from left to right, and these are different types of animals. And you see that human is in purple color, I believe. And you can see that this range is different between different animals, like see the cat here, mouse here. And if you think about, again, comparing human auditory field in terms of the frequency that we can hear, you can see that in the scale and compare it with other animals like elephant, cat, dog, and others. And as far as I know, even during someone's lifetime, this changes slightly. Like, I believe that before 25 years of age, you can hear some, like, you can hear the sounds like that are like in the lower frequency. Or if I'm not, I mean, higher frequency, yes, higher frequency, I think. That you can hear like sounds that those after 25 cannot hear. And it's a small range, but even in that range, if I play a sound here, it's very high frequency, so it's like or something like that. And then you can hear it, I cannot hear anything. Or if you search the internet, you can find those sounds. And that's one thing, for example, to consider about human auditory system. And also, in addition to frequency, another thing to consider is sound intensity. It's simple, but how loud the sound is being played. And if it's more than a level, as you can see, more than 80 decibel, it hurts human auditory system, basically. So we should aim for using this below 80 decibel. Again, you don't have to memorize these. This is just to give you an idea of why we should consider these factors. And if you put frequency and intensity together, there is like a 2D plane of what we should use in any system that we want to develop. And you can see the conversation is like some part of this auditory field, but it can go outside of this. And the X is frequency and Y is intensity. And you can see the limits of human perception of what we can hear. And also, just like in visual perception, there are familiar sounds that it means something to people. So if you use those sounds in a simulator or in a system, it's simply because people have prior familiarity with those sounds, they know what it's the sound of this or that, for example. Like the alarm of a clock or something. So again, the reason that we have to know about human auditory system is because of factors such as frequency, intensity, and similar factors. Now, within the same intensity and frequency, if you think about it, what distinguishes different sounds from each other is something that they call timbre. And timbre is, if you think of waves, the shape of waves determine the type of sound. Like what distinguishes my voice from your voice, for example, is this timbre. And if you want to replicate a sound in the real world in a simulator, you have to take care of not just of the frequency and sound intensity, but also timbre and similar factors. Like the wave might be something like this. This part that is repeated in every cycle, this shape is the timbre of that sound. So these are the factors that you have to keep in mind. And to some extent, it becomes technical because it's just the science of reproducing high fidelity sounds, which is itself acoustics, and its own, it has its own major, and people study that. And also, it's also studied under what is called as psychophysics. But just to have a general understanding of how these things work. So, do you have any question about auditory system, sounds?
My name is Chris. Would you say that haptics would also be an important part to?
Yes, we're going to talk about that later in the lecture. Yes, that's one of the factors, one of the main 5 senses of human. So perception, auditory system, haptics, these are all important. So now before going to haptics, yes?
So for sunlight, I know that all of these are machines to detect them, but for the human visual system, how do we make sure that we're very precise with like the views and put into our simulation?
You mean if target environment looks like something, how do we replicate that thing in the simulator?
Yeah.
So there are things like virtual reality tools that they use, like you wear these eyeglasses or goggles or whatever it is, and then you see the environment just like you are in the target environment. That's one way of replicating that. I would say also in simulator, what we know as simulator, it can be like a large room, for example. And imagine military operation. They make like a small, say, town or city or neighborhood looking like the actual battlefield, and they practice inside that. or they try to come up with those things. So if the view, like in a larger scale surrounding matters, they try to replicate that in high fidelity system with those techniques.
But then wouldn't it be still like limited because when they're designing the virtual reality, it's like based on what? Like based on our descriptions from experts, or because the error vision is like you know, like how do you detect like how much you can see, and then you do like virtual a really precise virtual reality. Does that make sense?
Yes, I think you mean that we can never 100% replicate the target environment in any simulation.
And like, is there a way that we are improving it?
Yes, I mean, mostly by using more sophisticated technology, and also by using certain tools, replicating certain tools, again, with the use of technology. And that's basically what we are talking about in terms of high fidelity systems near transfer. And they are doing that. Of course, any simulation, anything that is used or defined as simulator or simulation can never be the reality itself. It's still simulation, and people recognize that. And human recognition system, or in terms of perception, is so powerful that detects the smallest difference between simulation and reality. But this is the effort to create this. And also, even if they cannot create the exact replica of the target environment in simulation, they try to create this psychological atmosphere in people, even in game, that yes, everybody knows that we are in game now, but let's treat the game as reality, or at least if we can learn something from this game that can be used in reality, even that is a lot. So yes, it can never reach that level of realism of the target environment, but that's the goal, to get as close as possible, at least in our discussion in near transfer. Any other question? So after visual and auditory, now there's one question that we said we have to study human perceptual characteristics or human perception. And the question is, why should we do that? Why we just don't go to the target environment, see colors, just copy those colors, and then have the same colors or something in the simulator or wavelength or other things? Why do we study human perception? Why not using like physical measures? Like if you think of colors or human vision, why don't we use this physical scale that is established in physics for years? That you see the colors and the wavelength of colors. Or if you think about hearing, why don't we use this physical scale of sound?
Things on that, and I think it's because each person perceives vision and hearing in a different way. So, take a number, wavelength, it might not be representative of their trade population.
So because different people perceive it differently, and the trainees population might not entirely perceive things as the designer want them to. Yes, that's one factor. Any other thought? Yes.
Probably that the perception of humans is not at the same scale of the physical world. For some sections, humans are more vision. For some sections, human eyes are sensitive. But and this is just
Yes, exactly. That's right. Human perceptual system does not see things in physical scale, in a sense that we measure things with our measurement tools, But when you come to the physical human perception of those things, then you have to bring some modifications because we do not see things, for example, as you mentioned, here we see this entire spectrum over one dimension, or it's just there's no difference between this point and this point, for example. But human perception is not like that. We see things, or our sensitivity to certain ranges of things are different than physical measures. Any other? Yes, basically that's the answer, because there is no one-to-one correspondence between the physical measures and human perception. We have these measurements in physics, but then if you want to make them for human use or in any interface, then you have to take care of how we perceive them. That's what matters. So we do not concern ourselves that much with physical measures, wavelengths, frequencies that much, but with human experience, human subjective perception of those. And that is why human perception and studying that perception is more important. So just to clarify this, here I have an example. And I play a sound, and if you can just try to listen to the sound. It's a bit a strange kind of sound, but just try to focus. So it's like, oops. Yep. So, but if you depict the same sound in terms of wavelength, it's basically the same thing, repeating and repeating and repeating. But we hear it as something like going down. And just, again, if you watch the same thing in terms of wavelength, it's this. So nothing's going down, actually. It's the same thing. So that's one example, that we might hear things that do not correspond with the physical scale. Or our perception might be inaccurate if we just depend on physical scale. And what I just played is famous it was found by a guy named Roger Shepard, the psychophysicist. If you're interested, you can just search the name and find other examples. He found many examples of auditory and visual illusions, and it was basically his research. So basically what matters to us the most is human understanding of the environment in simulation instead of physical measurements. We are interested in human perception. And again, you have to keep this goal in mind because our goal is to replicate the reality in a simulator. And to understand human understanding of the environment, we need to know about human perception and not physical measures. So this thinking in terms of the distance or there's any or lack of correspondence between physical scale and mental scale, it kind of reminds us of the psychological and physical space that we talked about here. That again, there is a mental space or psychological space, and there is a physical space. But here, in terms of human perception of visual and auditory things, there is no such correspondence. Or there can be correspondence, but it's not like one-to-one. That we would say the distance in physical is this, it should be this in perception. No, it doesn't have to be that. Often it's not. Or the same thing holds for human tone perception, that if you, like keys of a piano are designed in a way that human perceive them or hears them as almost equally distant from each other. But then if you measure its frequency, the frequencies are not equally distant from each other. So things that we need to know to build simulators that look and feel realistic. The first one was visual system, the second was auditory, and the third is motion perception, which is another factor. It's not about human senses. It's not one of human senses, but it's more like in a psychological level of human experience. And what we need by motion perception is something like if you think of a flying an airplane, a flight simulator tries to replicate that movement or that gravity or different kind of movements of an airplane. Or if you think about acceleration and perception or the experience of acceleration and speed, that certain maneuvers mean certain different things. That if you think of, if you do not account for the activity of the engine in this picture, this one is when a helicopter is, for example, descending, it's accelerating because it's gaining speed because of the gravity. This is constant velocity. And when it's going up, if you think about this same thrust of engine, it's basically decelerating. And that's why if a helicopter is trying to go higher, it doesn't go like in a straight line. It goes, dives, goes, dives. It goes like in different cycles to gain more elevation. And this is not just for a helicopter, but fighter jets and other. So this is just basically trying to show that a simulator wants to replicate reality, has to replicate the human perception of motion and gravity and speed and acceleration and those vectors. Or another thing is simulation sickness, which is something that those who do research on simulators, training simulators, know that there is such thing as simulation sickness, especially for people who use things like virtual reality, augmented reality tools, that suddenly they feel like nauseated. Or if you've ever had the experience of being car sick, some of them feel like they're car sick or feeling like that because things are moving in their surrounding and they feel like they're staying in the same place. So that's another factor. So knowing about motion matters because of these factors like perception of speed and acceleration and simulation sickness and those factors that we talked about. So this one is, the next one is haptic perception, or the next sense of human senses. And just as one example of why, for example, we should know about this or have a general idea about it, is because of something like paradoxical cold. That you might have like hot water, or you might have the experience of, especially when you just touch that hot water with your foot, at first you feel like it's cold, but it's the opposite. So human perception might be deceptive at times, or sense of touch. Or as another example, it is simulating the touch and control of, this is the handling tool of helicopter, what they know, I think, as cyclic or something like that. And then this is the simulation of the same thing used in simulators. So the kind of like touching buttons or those things that if someone is expert in using that type of helicopter, is used to using that handling thing or that controlling thing in certain ways that it should be close to what the simulation is trying to simulate. Or again, pressing keys and buttons. This is like a system used to control drones. And of course, we have large scale military drones. And to practice that, you should have simulator, and that simulator should replicate that system as much as possible. So again, taking care of this factor might be important. It depends on the training system and our goal of building a simulator. It might be important because we might need to replicate the sense of touch for control. Do you have any question? of whatever we talked about in terms of these two factors like motion and haptic perception. Yes.
Really good. I was wondering if there was ever requirements where for certain like simulations, you have to test for someone with a disability related to what you can do it. So they might not know about it until that specific instance, like say with flying, I might do something with flying that I did never before that disability.
Yes, I would say that's an important factor, but usually they try to do that when they do trainees analysis or trainees needs analysis. So you might have certain systems that would say you have to have such and such physical characteristics to use that system. And then of course the corresponding simulator should also take account of that. But if it's something that we do not know the trainees population and they might have certain disabilities that might prevent them to use or might hinder their progress, then I think our focus should be on trainees, knowing trainees and their characteristics, or trying to present them with some questionnaires that if you know that you have certain disabilities, you should let us know before participating in that training session or training program. Yes, that's one of the factors that we talked about trainees analysis a few sessions ago. And we counted the reasons of why we should know about trainees and their characteristics. Any other question? So whatever we counted so far is usually considered as or categorized under a discipline. That discipline is called psychophysics. It's an academic scientific discipline, and their goal is to just basically investigate whatever we discussed so far. The relationship between physical stimuli and human perception and sensation of those stimuli. I know that some universities have that as a major, both in the undergraduate and graduate level. And most of their focus is basically on human threshold detection, of sensory threshold detection. And it is highly used in the design of systems and products, including training systems. And it's an important major, I think. And it has various types of applications in the design. So in addition to these psychophysical factors, of course, the original question was what we need to know to build simulators or high-fidelity simulators. The next factor is target environment. And we need to have an accurate understanding of the target environment. This is because it's our source, it's the main source of information that we have. And so we go to the target environment, do some field research with different techniques, for example, ethnography, video recording, filling forms, writing things, questioning, talking with subject matter experts, to gather as much information as we can from the target environment, tools that are needed, locations, other details, and context. And we gather that information because we have to replicate or take account of those factors in the simulator. And this is basically the same if you think about even computer games that think of like a first-person shooter game in like, say, Counter-Strike or anything that you have experienced. And it's basically adapted from some scenarios that happen somewhere in the world. And of course, when we bring that information, we need to have technical expertise to implement the simulator itself. And it needs basic engineering and programming and working with various types of graphical tools or animation softwares. And usually such an analysis are usually in larger scale is given to different teams. But a training scientist needs to be aware of these details or these steps of creating a training simulator. So just as in a bigger picture, first we need to know about human perceptual system, then the target environment, and then the simulator.